Hey. The wireless presenter?
Yes, use that because I've just found out exactly the story on why HDMI doesn't record. The gentleman just explained in detail. So with the Mac, you have to use wireless presenter.
Oh, it's the same for everybody.
It's for same. Anyone who is using the latest Mac will have HDCP enabled, and the Echo 360 books bans HDCP recording.
I always use
or any lecture theater anyway. Anyway,
Can the online students hear me? Hello? Can you hear me? All right. The assignment was due yesterday. So. Welcome back from the teaching break. All right. So today we are going to look at input-output. So far, we have been dealing with memory, main memory, and we've been writing programs, how to access memory, how to manage memory as a resource. And today we are going to talk about input-output. Now, why is input-output different from memory? We discussed in week 4 that CPU has direct access to memory, so we can use, the programmer can use load, store, or data movement instructions to manipulate whatever is present at specific locations in memory. There is no such direct access to the I/O devices, specifically the storage I/O devices, disks, hard drives. There are no instructions to directly, in one instruction, bring something from disk or write something to a specific location in disk. And this is due to the underlying architecture of computer systems. We need a lot more work to read, write information or data or files on disk. And if you remember week 4, we need interrupts and we need direct memory access, a mechanism for transfers between IO devices and memory. And this is how CPU accesses or programs accesses whatever is present in an IO device. First, the file or data is transferred from IO device to memory, and then the processor or the program can use regular load store instructions to access whatever is brought from disk to memory. Now, who should be responsible for initiating these IO transfers? This has been a theme in this course. Process running in user mode cannot access an IO device. And there are many issues with that. If we allow that, there are security issues, management issues, all of that. IO is a service provided by the operating system. So IO accesses are a responsibility of the operating system, and the user program using system calls requests the operating system, hey, I want to read something, I want to write something, I want to access an IO device. So if you recall the architecture, the transfers from disk to memory happen in this path, and then the CPU can access whatever is brought into memory. CPU does not have direct access to IO devices, to whatever is present on a disk drive or a solid state drive. That means programs don't have direct access to IO devices. User programs don't have access to IO devices. They must request the kernel, hey, initiate this transfer from disk to memory for me. And then the kernel obliges using system call, traps, all of those mechanisms. So this is what we are going to study the programming interface. So you, as programmers writing user level programs, can perform input output or can access IO devices. How to write programs to request IO services from the kernel, right? So Unix IO or IO in Unix-like systems, we are going to study that today. A file is a very basic abstraction in Linux, Unix, or other similar operating systems. A file is simply a sequence of bytes. And a lot of things that we intuitively don't think of as files are actually exposed as files in Linux. So devices, IO devices, disks, solid state drives actually appear as files. So here is a hard disk, which appears under / is a root directory. And then under dev, we have a device, SDA2. Similarly, there's a terminal, TTY2. This is where you output when you print something to the screen. And it appears as a special device. Even the kernel image, which is the compiled binary for the kernel, appears in /boot. And /proc, so / once again is the root, this is the anchor point. And then everything from that is a hierarchy. Linux does something clever to expose its internal data structures, some key data structures. It uses the /proc file system. File system is just a collection of files. All right. So this means if a lot of devices and a lot of different devices can be exposed as files, then we have a common API to manipulate the contents of the files. We are mostly going to limit ourselves to regular files. and more specifically the text files. The API we have is very simple. We need to open the file to tell the kernel that we want to do something with the file. We want to access the contents of the file. We want to read or write to the file. We have the read-write API. These are system calls. So every time you issue a read from the user level program using the system call read, there's a trap into the kernel, and the arguments, which we'll look at shortly, tell the kernel what kind of read is that, which file, how much data to move from the file on disk to memory. So we have read, write, open, and when we're done using the file, we want to close the file. So any data structures that a kernel is maintaining for the file, the kernel can actually delete them. This is important for management purposes. Each file has a file position. So this is more like a pointer to a specific location in the file. And each time we do a read or write, the file position is adjusted accordingly. Indicates next offset into the file to read or write. So if you do a bunch of reads, the offset keep incrementing. And when you do a subsequent read, the kernel knows where the offset is. You can also change this is called a seek operation. You can also change the offset by doing an else seek. If you want to advance to a specific offset in the file, you can use the else seek system call to change the offset of a file and then do a read or write. So file is just a sequence of bytes, and there is a variable inside the kernel that points to the current file position. Okay. So the key takeaway from here is we need to open the file using the open system call. These are all system calls. We need to do our accesses, whatever we want to read or write to the file. And once we're done, we should close the file. All right. And then from time to time, you will need the else seek operation to jump at some random location in the file. That will change the offset that is maintained by the kernel. So there are many different types of files. Regular files contain arbitrary data, your photos, your emails, your documents. These are all regular files. Directories is more like an array of links, and with each link points to a file or another directory. And sockets are used for communicating with a process on another machine. This is the subject of networking, and we will look at that next week. There are other types of files, pipes, links. We are not going to touch upon these. And character and block devices in Lab 7, you are either looking at it or you will look at it if you haven't done the lab already. We'll explain what character and block devices are, what is the difference, and how they operate. So regular files contain arbitrary data. Applications distinguish between text files that contain ASCII or Unicode characters, and then binary files. When you compile a program, the object file generated is a binary file. And kernel doesn't know the difference. If you read or write from a file, it just treats it as any other piece of information. Text file is a sequence of text lines. Each line has a terminating character, a new line character, which is \n. It's called the line feed. And other systems use a different representation for end of line. So in Windows, you have \r, \n. \r takes you to the beginning of the line. It's a historic thing, comes from the days of the typewriters. So you have a lever with line feed, and then you have to move the carriage back to the beginning of the line. It's interesting if you ever want to search online how typewriters worked. But carriage takes you to the beginning of the current line, and \n takes you to the next line. So directories are just an array of links. Each link maps to a file name to a file. In Linux, each directory contains at least 2 entries. Dot is a link to the directory itself, and dot is a link to the parent directory. So file system, collection of files are organized as a hierarchy, and in this hierarchy we have parents and children. We'll look at that in a little bit. From the shell command line, you can use make dir to create a new directory, ls to view the contents of the directory, and to remove the directory, rmdir. Be careful with rmdir. You don't want to destroy, you don't want to lose information. Okay, so this is how a typical file system on Linux or Unix-like operating systems look like. You have a hierarchy which is anchored by the root directory named /. So / is root, and every file, every directory has a name relative to the root directory. Kernel maintains current working directory for each process, and you can modify that using the change directory or cd command. So path names. Absolute path names look like this. They begin with the root directory, and they list the all the directories on the way. So here we have hello.c, so / home draw hello.c. So this is an absolute. It's starting from root all the way to the file name. This is an absolute path name. And then there is the relative path name. So imagine you are in a directory called home Bryant, right here, and you want to access a file hello.c. So what you will do is you will go to the parent ... in the previous slide here. So ... is for the parent. So you do ... to go to home, and then home draw hello.c. So this is a relative path name. This is relative to the directory you are currently in, the current working directory, which is home Bryant, right? The absolute path name is starting from the root / home / draw. So when we open the file, we inform the kernel that we want to do something with the file, and the kernel returns us an integer, a positive integer, which is a descriptor that you can use later in the program for accessing the file. So when you make the open system call, this is a system call. you're opening a file, in this example, using the absolute path name of the file. And the next argument is the flag. And the flag argument tells the kernel how you expect to access the file. Do you expect to read the file, write the file, or both read or write the file, right? You could, but it wouldn't make much sense, right? You can do these things. Right? All right, so the flag argument, the second argument of open is the flag, and that tells the kernel what you expect to do with the file. If the programmer doesn't want to write something to the file, it is safe to open the file using the read-only argument, right? If the return value is less than 0, there is some kind of an error. The file descriptor cannot be less than 0. And here we are checking for the error and printing something and exiting. So this is a descriptor. We don't want to carry with us when we write programs, the file names. We don't want to remember file names. We just want to open the file once, obtain a descriptor from the kernel, and then use that descriptor to do everything with the file, right? This is the idea of the open system call. So each process created by the Linux shell has at least 3 descriptors, or 3 open files associated with a terminal: standard input, standard output, and standard error. The descriptors are 0, 1, 2. So every process, whenever you fork a process, you get the process has these 3 descriptors, these 3 files by default opened for itself. Standard input is for providing input to the program, usually via the keyboard. Standard output is to write something, whatever the program outputs using printf or any other statement is printed to the terminal, and the terminal is represented as a file because everything in Linux is a file, and the descriptor of that file is an integer 1. So, and when the process opens more files, it obtains from the kernel a descriptor 3, 4, 5, 6, 7, right? And then you can use the integer variable to do a number of things with the file. Once you are done using the file, you have to close the file, and you need to provide the descriptor that was returned to you when you opened the file. Okay. So you should not be closing an already closed file. This has the same consequence. Undefined behavior, if you're free, a block for which there is no corresponding malloc. This is a similar kind of an error. All right. So how do we read from an open file? Once the file is open, we can now use the read system call to read something from the file. So we need to provide the file descriptor that was returned to us after the open system call. And we need to provide a buffer. A buffer is just a character array in which the kernel will copy the contents of the file. And this is how you get something from a disk, for instance. So you have a file, you open the file, you provide a buffer as part of the argument to the read system call, and you provide how much you want to read from the file. Here we want to read, the programmer is telling the kernel, I have an open file, the file descriptor is fd, and read 512 bytes from that file and transfer them from disk to memory. And you know at this point that when you create a buffer like this, a buffer is just for holding some data that is returned by the kernel. This character array is in memory. So the kernel will bring 512 bytes from the file, which is on disk, and copy 512 bytes in this buffer character array that the programmer has created. And the programmer has given a pointer to that array as part of the argument to the read system call. So 3 arguments. Which file do you want to read from? Now you don't want to give the path name, that's too cumbersome. You already opened the file using the relative or absolute path name. Now you have a descriptor. Now you should use a descriptor for all subsequent operations on the file. Here we are trying to read 512 bytes from the file, which is on disk. So we tell the kernel, we cannot do it ourselves. A user program cannot do it itself. It has to request the operating system using the system call read. Here's the file descriptor. Here is a buffer. I have already created the buffer. If you don't create it, something bad will happen, right? Here is the size. Here is how many bytes I want to read. And the kernel will oblige. It will fill the buffer after some time by doing the transfer from disk, reading the file. It will fill the buffer with 512 bytes. The idea of buffer in today's lecture is quite important. So remember that a buffer is an array where you want to store the contents of the file. In this case, this buffer is created by the programmer. And what is returned as the return value of the read system call is how many bytes are read from the file descriptor. S size underscore t is the signed version of size underscore t, which should have all used in the labs. Less than 0 return value indicates an error, and you need to check for the error. There are a number of reasons why the kernel may not be able to give you 512 bytes. The kernel may not be able to return 512 bytes or whatever number you request. And when that happens, we call this condition short counts. Short counts is when what is returned by the kernel as part of the read system call is less than what the programmer asked for. This is not an error. This is not an error. This is a condition. The programmer may not know that the file doesn't have that many bytes. The end of the file is approaching, but the kernel knows that. If the programmer says, give me 512 bytes, and there are only 500 bytes, then the kernel will only return 500 bytes because there is nothing after that in the file. And we call this condition short counts. Now, short counts, this is one way, one example of short count. They could happen due to other reasons. The process may be, or the read system call may be interrupted by a signal handler or something else. There are a number of things that may happen, and the read system call may be interrupted. The kernel does not reissue the read system call on behalf of the programmer. So it will just return a short count. Okay. And the programmer has to check if something went wrong and there is a need to re-execute or make the read system call again to get the remaining data. Okay, so we will come to short counts in a little bit. Let's first look at the write system call. So write system call is the opposite of the read system call. Same arguments, file descriptor. You open the file, you have a file descriptor, you're not performing. You're not writes are destructive in computer systems. This is an example of. You're now performing a write system call. The first argument is a file descriptor. Once again, you are providing the buffer here. The programmer is providing the buffer, and this is the size of the buffer. Now, in this example, there is nothing inside the buffer, but typically the programmer will fill the buffer with some data that they want to write to a file, and then they will tell the kernel by making the write system call, hey, there is something in this buffer, and I want you to go write this to the open file, which is represented by the file descriptor. And because each file has a position, has an offset that is maintained by the kernel knows where to write. Wherever that file position, wherever that offset is, the kernel will just go and write. And if you want to write at some random location, as long as you know what you're doing, you can first use the seek operation, the else seek system call, to go to a specific offset and then do the write system call to tell the kernel to write at a specific offset in the file. So read and write system calls, in lab 7, you will be doing this a lot. They're very simple. You open a file, you get a file descriptor from the kernel. All you have to know is the path name of the file and that you want to open. And then you do the read and write. You make the read and write system calls. 3 arguments, very simple. File descriptor, buffer, you need to create the buffer. If you don't have a buffer, you know what will happen. You're all malloc experts by now. And then the size of the buffer. As usual, if n bytes, if the whatever is returned as a result of the write system call is less than 0, it's an error. The short counts are still possible, and they're not errors. So here's an example. Once again, we are looking at this API, which is part of that comes with the book, cs.app.h. They automatically handle the errors for you, so you don't have to write p error and you don't have to check for the condition. It's with the same system call, the capital first letter, if you recall. So what they're doing here is, in a while loop, they're reading something from standard input. This is just a convenient constant that is defined in a header file, I think. And this is just 0. Std out is 1. So they just gave these descriptors names, so you don't have to type 0, 1. It's more readable this way. So this program is reading from standard input into a character C. So this C here is a 1 byte buffer. It's still a buffer. It's just a 1 byte buffer. You use a read system call to read a character from standard input. So 1 means 1 byte. This is the third argument, is how much you want to read. And you write it to standard output. So this is a character you want to write and 1. And be careful about the second argument. It's a pointer. It's the address of the buffer, not the variable. So this program copies standard input to standard output, 1 byte at a time. So short counts can occur in many situations. As I was saying, when the end of file is reached, There is no explicit character or marker to represent the end of file in Unix-like operating systems, at least in Linux. It's just a condition. When you reach the end of file, it's a condition that is detected by the kernel. And you can check for that condition if the return value of read is 0. Okay. If you're reading text lines from a terminal, you don't know how many characters the user is going to type. So you just randomly tell the kernel, read, I don't know, 1024 bytes, and the user only types a few characters. You're going to end up with short count. So these are all examples of short counts. It happens a lot when you are communicating over the network with a different computer. A lot of things can go wrong, and we will see that in subsequent lectures when we do networking. When we deal with sockets, socket is also just a file. So the remote connection to a different computer in Linux is just a file. You know, you open the file, open the remote connection, and you get a descriptor the same way you get a descriptor for a regular file. We'll do all of that next week. And then a lot of things can go wrong. Errors, wires, you can imagine there's so many things going on between two computers that you can end up with short counts. You know? So we want to write our programs in a robust fashion so we can deal with short counts. If we know that a file has a specific number of bytes and we really want to read that many bytes, we should check for short count and we should reissue, keep making the read system call until we get the number of bytes that we want. Okay, so dealing with short counts is the programmer's responsibility. There are a few situations where short counts do not occur when you're reading from disk files, except for end of file, and when you're writing to disk files. All right, so now we're going to look at a robust I/O package. So this is once again part of your API that we provide you, cs app.h, and the corresponding C file is csapp.c. So you'll be using that in assignment 2 and in subsequent labs, networking and all. We don't want you to use the read and write system calls directly. I'm going to explain how the robust I/O package implements wrappers for those system calls, allowing for short counts. And you are going to use these starting lab 8. So it's a good thing to understand what this package is trying to do. All right, so RIO stands for robust I/O, the set of wrappers that provide efficient and robust I/O. Making system calls directly is possible. As a programmer, you can do that, but it's not always a good idea. It's you need some high-level library, either the standard C library or this kind of package to deal with things such as short counts and other errors. So this package provides two different kinds of functions, unbuffered input and output, and buffered input of text lines and binary data. So I'll explain a little bit what is the meaning of unbuffered and buffered. So these are the functions that we're going to look at. N means unbuffered, and B here means buffered. So these are the routines we're going to look at. So let's look at unbuffered robust I/O. Now, we will look at buffered routines in a little bit, but I just want to give you a quick intuition. This package, what they are trying to do in the buffered routines is they are trying to reduce the number of system calls by reading large chunks of data from files. System calls are expensive. And if you make a system call, or if you go to the disk to read just a few bytes, 1 byte, 4 bytes, 32 bytes, that's a very inefficient program or system. So in the buffered versions here, what they are trying to do is they have internal buffering, and they have very large buffers. And what they do is they read very large chunks of data from the file, and then they return byte by byte or whatever the user wants at a time. Right. It's like the arena, yes. So you don't want to do mmap, mmap, mmap all the time, hundreds of times. You just do it once, read a lot, get a large chunk, and then do. So reducing the number of system calls, read and write system calls, is very important. These are very expensive functions. System level functions are very expensive. The CPU stops doing whatever it is doing. It has to jump to another location in the code space, and it has to do a number of other things. Okay, so let's look at unbuffered. So the unbuffered versions handle short count, and they only return a short count if they encounter the end of file. If the end of file has reached, there is no way, there's nothing left, right? You have to return a short count. But these functions check for other kind of interruptions, such as interruptions by a signal handler, and they keep issuing the read system call again and again until it is clear that there are no more bytes left in the file. And there is a write end version of these. So here is how they have this wrapper, which has the same semantics, which has the same arguments as the read system call. So the same arguments as the read system call, a file descriptor, a buffer that is provided by the user or the programmer, and how much the programmer intends to read. Same arguments, it's a wrapper. Internally, what they are trying to do is you try to read as much as initially, you try to read whatever the programmer wants, n bytes. So here, you try to read n bytes initially. Here, they're checking for interruption by a signal handler. If there is an interruption by a signal handler, the read system call will just return with a short count, right? It will not do anything else. It's just one system call. What they are doing here is, in a while loop, they come back here and make the system call again until you read all the bytes that the programmer wants to read. As long as n bytes is greater than 0, you keep issuing the system calls. And this is something that the read system call, it's one system call, it doesn't do. And this is why this wrapper is more robust than using the system call itself. So when we did signal handlers, we know that interruptions can happen for a variety of reasons. The kernel might install the signal handler to check for interrupts. There could be interrupts. There could be a device that wants to communicate with the system, with the program. So in that case, the kernel has to decide, to interrupt whatever it is doing, and to handle the interrupt, right? So signals can arrive for a variety of reasons, right? And that was lab 4 or something. It depends. There are priorities. So certain kind of interrupts the kernel can ignore, and the kernel can mask certain type of signals when it is doing something critical. But there are other types of signals that the kernel cannot ignore, and it depends on the specific operating system, specific system. What are the things that the kernel can ignore, and what are the things where it has to interrupt whatever it is doing and go handle that kind of interrupt. So this is pretty standard program. If the error number is EINTR, which means that the system call was interrupted by a signal handler, you set nread to 0. Basically, you read nothing. And so here, sorry, that's not true. So if there's an error, if nread is less than 0, which means there is some kind of an error. If it's a signal interruption by a signal handler, you set nread to 0. Otherwise, you just return. For all other kinds of errors, you just terminate the function. And if nread is 0, it means the end of file. So right. If it's an interruption, you go back and re-execute, redo the system call. Otherwise, it's an end of file. And then you manipulate the buffer pointers and how many bytes are left to be read in the remaining code. What? All right. So as I was saying, so we will look at this this code in the labs. Here, I just want to give you a quick overview of so as I was saying, the motivation for buffered versions of the RIO read wrappers is most programs issue many small read-write requests. This is how programmers think. They think in high-level abstractions. They think of fields inside a structure. But the drawback of small accesses of reading or writing a few bytes at a time is you end up with a lot of system calls, and system calls are very expensive. So any good library, any good package that wraps read-write system calls should do some buffering or should try to reduce the number of system calls. So one solution is on each system call, you try to amortize the cost of the system call. You try to read a large chunk in a user level buffer. This buffer can be a separate library, or it could be part of the program that the programmer is writing. The library buffer can be very large, while the applications buffer can still be small. So now we have two buffers, one that is maintained by the package or the library. This buffer is extremely large, and the idea is to reduce the number of system calls, the number of times you have to go and read from the file. And then there is the usual application buffer that the programmer provides, where the bytes that the programmer wants to read are copied into. So now we have two buffers. The drawback of this approach is you have an extra copy between user level buffers. Copying is not free. Copying has a cost, but there's a trade-off. You reduce the number of system calls, but you end up with a few more copies. All right, so here are the buffered functions. So there is a special structure that encapsulates the buffer and a few variables that the package uses. To initialize that structure, there is the RIO read init b function, and then there are functions to read n bytes or read a line. So read line b reads a text line of max length bytes, and then there is the read nb that simply reads a few bytes. Okay, so I want to give you a key idea of how you implement buffering in a library or in a package. And we will look at the code briefly, but you will look at the code in the labs more deeply. So you have this buffer, and the key idea is this buffer is different from the buffers we have seen before, where the kernel copies the bytes read from the file. This is a buffer that is maintained by the RIO package. This is the name of the buffer. This is the buffer itself. And whenever the user calls one of these functions, read a line or read some number of bytes, what the package does, what the function does, it actually reads, it actually tries to fill this buffer. If the user says n bytes, it reads some number of bytes, n multiplied by, I don't know, 16 or something. The idea is that, you know, in one system call, you read as much as you can. So the next time someone calls this function again, you don't have to make another system call. You just return, you just copy bytes from this buffer to the buffer provided by the programmer. So the buffer at any point has a buffer pointer, which points to the beginning of the bytes that haven't been read yet by the programmer, but they have been transferred from the file on disk into this RIO buffer. So some number of bytes have already been read. These are bytes that the programmer has already seen. This is a pointer to the beginning of the data that hasn't been read. And the RIO count is how many bytes are left unread, starting from the buffer pointer. So if you think of file, the way this buffer is layered on the Unix file, some bytes in the file are not in the buffer. Some are in the buffer, and out of them, some have been read already, others not, and there are some bytes that are unseen that will probably be buffered into the RIO array at some point. So this is how you have a file on disk at the bottom, and you try to layer a buffer on top of it, and you try to read as many bytes as you can in one system call. You copy it here, and then you return to the programmer, let's say n bytes at a time, until you run out of bytes in the buffer, and then you make another system call. So this is how you amortize the cost of the read system call by reading a large chunk and returning to the programmer n bytes at a time. And so now we have a transfer from file on disk to this buffer, RIO buff, and then from here to the other buffer, that is the argument of the second argument of these functions. So now we have an extra copy, but we prevent making too many system calls. Right, so there are certain restrictions, right? So if you mix buffered RIO functions with unbuffered RIO functions, it's not safe, because the unbuffered versions will move the file position, and the buffered version will get confused where the file position is. Okay, so there are certain level restrictions that come with this kind of high-level IO packages. But the key idea is that there is a trade-off here between how many the cost of a system call and the cost of an extra copy. And the cost of a system call is way more than an extra copy, at least as long as the copy is a few bytes. Okay, so I'm not going to go over all the code that is used to implement all this. The key data structure is a struct RIOT. This is a buffer that I'm talking about. This is a buffer we are talking. This is the extra buffer that is maintained inside this package. This is not a buffer provided by the user of this package. The read system call has no such buffer. It goes directly to this, and it brings and does a transfer. Here, the writer of this package is trying to have internal buffering, which is transparent to the user. The user of this package doesn't have to know what is going on inside. We are just speaking in because we have the code, right? You don't have to know what is in the package. This is a buffer that the package has created. And each time there is a call, they try to fill this buffer as much as possible. And then they have these pointers, the start of the buffer, the file descriptor, and RIO count to remember how much is left in the buffer before another system call brings more data from the file. So all the information is contained in a struct. And this is how you can use the package to read a line from a copy the lines of a text file from standard input to standard output. So here you initialize, and then while you don't reach the end of file, read a line and write it to standard output. This is an example of how you can use the package. So your homework is that, so csapp.c and csapp.h, we used it once before. We will be using it in the rest of the course, in assignment 2 as well, for sockets. And you have to read the code for these 3 functions and understand it, what is happening in the code. So I give you a brief overview. So what they're trying to do here is you see that whoever is using the RIO read function is asking for n bytes, but the function itself is making a system call and reading not n, but a different number of bytes. It is, and this is the buffering I'm talking about. It's not reading n bytes. It's reading way more. This variable here, RP dereference RIO buff, the size of this buffer could be 1024 or much larger, and n could be just 1. The user of this function could say, give me 1 byte. Internally, whoever wrote this function is trying to read 2048 bytes and trying to reduce the number. So next time, 1. So I'm not writing all the other arguments. 1. So this would be a system call, but this will not be a system call. The second read can be satisfied from the buffer that is created by the package writers, whatever that is, RIO buff. And this is the extra mem copy as a result of this optimization. So as a result of this optimization, where you're trying to reduce the number of system calls, nothing is free. There's no free lunch. You end up with an extra mem copy. The read system call fills this buffer, and then there's a mem copy. In the examples we saw earlier, unbuffered versions, the read system call would just do 1 copy, fill the user buffer. All right, so this number of copies, number of user buffers is obviously confusing. It's confusing, but this is what it is. And we will see, we are going to see more buffering. So more and more layers of buffering will happen. And in the labs, you might have already seen double buffering, triple buffering, and all that. So how much time do we have? Half an hour. So there's a lot of metadata associated with a file that the kernel maintains. And you can use the stat and fstat functions to learn something about the file. Understanding the entire structure is a subject of operating systems, but in a struct stat, there's all this information about the file, user, owner, time of last access, number of blocks, total size, device type, and all that. And you can use these functions. So stat, once again, S capital, they're checking for errors. We are using the books API. The system call is as small. You can check if a file is a regular file using certain macros, and these macros are defined in cs.stat.h. So you don't have to memorize all this. This is all in your lab spec. So cs.stat.h has a number of macros to make it easy for you to check if a certain file is a directory, a regular file, or any other type of file. All right. So these macros are useful. And then you give as argument stat.st mode, and you use a stat system call to initialize the stat structure for a specific file. So here's an example. When you run this function, you provide a file. It's a regular file, and you have read permissions. Then you can change the ch mode is used to change the mode or the permissions bits of a file. You can change the permission, and then when you read on the program, you no longer have the read permissions. All right. So we have been doing this. Every time we look at the API, we have a brief peek into the kernel data structures that actually provide that abstraction. So how does the kernel provide the file abstraction? There are three key data structures: the descriptor table, the open file table, and the vnode table. So the descriptor table is for each process, and it has it's an array which is indexed using each of the open file descriptors. So the first three are taken by the standard input, standard output, and standard error, 0 and 2. Each of the entries point to another table called the open file table. And for each open file, it has a bunch of information about the file, file position, how many processes have opened the file, which is reference count, ref count. Okay, and then there is the vnode table. So the first entry in the open file table points to the vnode table entry, and this is all the information in the stat data structure. Okay, so these are the three tables that the kernel uses to provide the file abstraction. Implementation and reasoning why we have these three tables is operating systems. We won't do it here, but you need to know how the abstraction is provided. Otherwise, it looks like magic. Once again, just like virtual memory mappings, this is just a bunch of data structures. The abstraction is provided by having a few data structures. So file sharing, here are two distinct descriptors. You can open the same file twice in the same program. And the idea is that as long as you're careful and you want to read from different file positions, from different positions in the file, you can do that. So part of the program could be reading from a specific offset, and the other part of the program could be reading from a different offset. And they both have distinct entries, distinct descriptors, entries in the file table, but they both point to the same entry in the vnode table. So the vnode table is the structure that maintains one data structure for each unique file. So how we do this every time how fork, a child process inherits its parents' open files. So here is the parent, which has this file 4 descriptor open, file B is open. And after the fork, the child gets an exact copy of the parent's descriptor table, open file table, and vnode table. The only thing that changes is the reference count is now 2, because now the parent and the child are both have these files open, so the reference count increases by 1. And they both must close each of the files for the kernel to destroy all the data structures. This is the thing. So after fork, child gets an exact copy of the parents' tables that provide the file abstraction. IO redirection. So in Linux, you can redirect the contents, the output of a command or a program to a file on disk using the greater than operator. So this is called IO redirection. Instead of whatever the program was going to print on the screen will now be sent to a file on disk. So here foo.txt is a file on disk, and ls is a command that lists all the files in a directory. If you redirect the output of ls to file foo.txt, you will not see the output on the terminal. It will be redirected to the file. And this is a very powerful mechanism provided by Unix-like operating systems. What happens? So also you can have a program that reads input from keyboard, And you can actually use the other operator less than to read from a file. So IO redirection goes in both ways. You can redirect the output of a program or a command to a file on disk, or you can read from a file on disk instead of reading from the keyboard. How the kernel implements that is interesting. There is a dup2 function which copies the old file descriptor to the new file descriptor. So let's see an example of that. We have this descriptor table before dup2. The descriptor of FD1 is A, FD4 is B. And after dup2 duplicate to 4.1, from here to here. So now from here to here, they both are B. And this is a mechanism the kernel uses for IO redirection. It's really very simple. So step number 1, the child process whenever you run a program, you remember from the shell lab, you have an exec system call before a fork. So we have this file standard out that points to this entry in the file table and vnode table. So what you do is, and you have this open file where you would like to redirect the output. Instead of standard out, you want the output to go to file B, which has its own data structures. So what the kernel can do, it can just point the FD1 standard out to file B and destroy these structures. And so now instead of the output going to standard out file descriptor 1, it will go to the file that has a descriptor 4. So these kind of operations, once the kernel has this abstraction of a file and these data structures, tables, it can do these kind of things to give such mechanisms like IO redirection. Okay, so standard IO, C standard library that you have been using, it actually has the same motivation as the RIO package. The key idea is you want to give high-level abstractions that handle short counts and you want to enable buffering. The standard C library routines have buffering. These are buffered IO operations. So instead of open and close, so system calls open, close, you have f open, f close, f read, f write, and then you have a bunch of other functions, and you have used scanf, printf. There are also wrappers of those functions. These are all buffered functions. So in standard C library, there is this concept of streams. Stream is just an abstraction of a file descriptor and a buffer in memory. So the RIO package has had this RIO buffer. Standard IO streams also have an associated buffer, and it's trying to do exactly the same thing that RIO package is trying to do. It's trying to reduce the number of system calls, reading a large chunks from file and doing internal buffering, both on the read and the write path. So C programs, once again, have 3 descriptors associated with them after the fork system calls. Similarly, they have 3 streams associated with them. And a stream is initialized with the file keyword. So here we have we can create a new stream and then use fopen, fclose, and all those functions. Right, so just like the RIO package, the standard library has internal buffer, some of which is already read, other is not read. It uses read to grab blocks of data, refills the buffer when it is empty. So IO calls are expensive, as I was saying, 10,000 clock cycles. This is a lot of time. You want to avoid as many system calls as possible. Applications, especially applications that manipulate text files, often read 1 byte at a time. So you want to read 1 character and then check if it's end of line. And then you want to read another character, end of line, another character. So this is very expensive if you don't do buffering. If for every byte you keep using system calls, this is very expensive. Text manipulations are ubiquitous in search engines, in databases, and there buffering really helps. And standard C library is more advisable than native system calls. So we say native system calls when you issue read and write up functions which are system calls, and these are high-level abstractions on top of them. So here's an example of buffering that a standard IO library does. So if you have a program and you say printf HELLO, it will only write to the terminal when an end of line is encountered or when you execute a special function called fflush. It does buffering. That's why when you use printf in your programs, sometimes funny things happen. You don't see the output right away because there is internal buffering that is going on. So in Linux, in the labs, there is a function, or there is a tool called strace that you can use to see what the shell is doing and what the kernel is doing. So if we run this program with strace, we will learn what happened exactly. So the exec system call and then the write system call. So here it's not doing 1 write for each character. There is no correspondence, but one-to-one correspondence between printf and write system call. There's 1 system call for 6 or how many are these printf statements. So it's doing internal buffering and then doing 1 system call. Okay, so Unix IO is here inside the kernel. And on top of that, we have seen today standard IO functions and RIO functions. And then programmers typically have a buffer, a small buffer that they maintain whenever they want to read something from a file. So from the kernel space, it enters a buffer maintained by these packages. And from here, it goes to the second buffer that the programmer provides. These are the functions. You will look at the code in the labs, and as part of your homework, some of these we have already seen, others we have not. And remember that the distinction between system calls and high-level functions. These are system calls, and these are standard IO library functions. They do buffering. So there's an extra copy here due to the internal buffering. And these are native system calls. This is, use them as long as you know what you're doing. You will have to deal with short counts, and there is no internal buffering. There is something inside the kernel called the page cache. So there's an extra level of buffering, and this is the last level of buffering today. There's no more buffering after that. The OS is smart enough. The block devices, disks, solid-state drives, they are really slow. In fact, you can't even read. These are not even byte addressable devices like main memory. These are block devices. You need to read at least 512 bytes or 4 kilobytes. And when we looked at disks and how they operate, we already saw that the smallest addressable unit on a disk is a sector. And the operating system is smart, knowing that all the mechanical movement and everything is very costly. It actually reads 4 kilobytes at a time. So even if the read system call is issued and the programmer wants to read 1 byte, the operating system is smart enough to read 4 kilobytes with the expectation that soon the programmer would want to read the rest of the bytes. Anytime we have this optimization, we call it cache, right? And this cache in the kernel is called the page cache. It's called the page cache because page is the smallest unit that a kernel uses to do memory operations internally. Typical page cache, page size is 4 kilobyte. And so this is just a cache of 4 kilobyte pages. So there is the disk transfer. There is the disk transfer. There is the copy from the kernel page cache to the RIO package. And then there is the copy from the RIO to the buffer provided by the user. So disk transfer plus 2 copies is typical in this style of IO. Now, sometimes you could be smart, and if you know what you're doing, you can give up on standard C library, RIO packages, and you can say, look, I know what I'm doing. I'm just going to use a native system call. I don't want to pay the cost of an extra copy. I'm smart enough to know. Okay, usually programmers don't do that. They use high-level packages, standard C library, and they pay the cost of extra copy. So in lab 7, if you haven't started already, you are going to reason about these trade-offs. We are making you think about these things. The second style of, so all of this, what we did today, so is called syscall IO. You use explicit system calls, read, write, to initiate disk transfers. Now we know that there is a second style of IO, and we have already seen that. And let me refresh your memory, MMIO, memory mapped IO, using the mmap system call. So in your assignment, you have used the mmap system call with map anonymous. So there is no backing file, but you can use the same mmap system call to back a part of your virtual memory by a file. So this is your process virtual memory. You can use mmap to reserve a portion of your virtual address space and tell the kernel that this is not backed by anonymous pages. This is backed by an actual file on disk, right? And this is lab 7. You will write programs where will you back, or you will have a portion of your address space, which is, and behind that is an actual file. Okay. This is a system call. It returns a pointer. You can provide an address if you know what you're doing, but typically let the kernel pick the address in the virtual space where you want this mapping to take place, to appear. The length of the mapping, the flags, expectation in terms of if you want to read or write this specific file, and then the file descriptor. You need the file descriptor before you make the mmap system call. So this is a style of IO where you don't have to use the read and write system calls. You use mmap to create a mapping in your virtual address space and provide a file descriptor to tell the kernel that behind this mapping is an actual file. Once the mapping is reserved, the moment you try to read or write to any address inside this mapping using regular load, store, or move instructions, there will be a page fault. We know a page fault, how page faults work. There will be a page fault. But this time the kernel will know not only do I need to find a free physical page for this mapping, I actually need to transfer something from disk into physical memory, because this portion of the virtual address space is backed by an actual file on disk. So the mmap system call gives enough information to the kernel about the fact that this mapping in the virtual address space is actually backed by a file. And when there is a page fault, the moment the programmer tries to access any address in that mapping, the moment there's a page fault, the kernel can look up, hey, I need to find a free physical page. I need to fix the page table entries, PTEs entries for the virtual to physical mapping, and I need to transfer something from disk. Okay, so MMIO is a very powerful mechanism. You see that this system call returns a pointer. At this point, the programmer can use the pointer to do disk IO. So imagine that, suppose that mmap returns a pointer, ptr equals mmap, whatever, all the arguments, file descriptor, something, and all that. When you do ptr 32, just an example, behind the scenes, there is a disk transfer going on, but the programmer can use the pointer to access the file. The transfer is kind of transparent to the programmer. You are no longer making explicit read and write system calls. Once you do the memory mapping using mmap, at this point, you are using the pointer to go to different portions, to access different portions of the file. And behind the scenes, the kernel will do the disk transfer for you automatically. Now, what we are doing here is, the drawback of this approach is nothing is free. You avoid the overheads of system calls, but you pay the overhead of page faults. Page faults are also expensive. We spent a week on that. You have to do a TLB access, you have a TLB miss, and you have to do a page table walk, you have to do this, you have to do that. So in memory mapped IO, there is the convenience that you are dealing with pointers, and there is no longer a distinction between whatever is returned by malloc and manipulating the disk files. You are using pointers for everything. And this is very powerful for the programmers. They don't have to think about, hey, I need to issue a read system call, I need to issue a write system call. They can just write ordinary regular programs, and disk transfers will happen behind the scenes, and whatever mappings are anonymous, your malloc that you have written in assignment 1 will take care of that. The drawback is the overhead of page faults. In the other scheme, the drawbacks is system call and a number of copies. And in lab 7, we let you reason about all this. You will write programs using syscall IO, using MMIO, and you will think about how many copies are happening in each case and what is the overhead of a specific program that you are writing. If you haven't started the lab, please start early. And the rest of the slides are for your own reading, some advice, which packages to use when. My advice is to think about performance, to reason about performance, how many copies, overhead of system call, overhead of page fault. It's not always easy, but that's what we're learning here. Thank you, and I'll see you next week.
So you just skip the Thursday with the Queen.
Huh?
You're just skipping the Thursday with the Queen.
Yeah.